The last and most promising approach we will study in this course for solving the SLAM problem is the graph SLAM. A graph is a very important data structure in mathematics, computer science, and also in robotics, and is commonly used in many applications from planning and logistics to communications and, of course, computer science. A graph is simply a set of nodes, also called vertices, connected by lines that are also called edges. Depending on the specific application for which they are used, each node can have a different meaning. It can indicate, for example, a city, and each edge that connects two nodes basically is connecting two cities and can be associated with a cost that indicates, for example, the distance between two cities. A similar graph can be used to solve the problem of planning routes that cross multiple cities by choosing the fastest one. An approach that solves the SLAM problem precisely involves using this data structure, the graph, hence is called graph SLAM. To understand how this algorithm works, let's start by considering an initial pose of the robot, a point that we consider as the zero, from which the graph SLAM functionalities starts. We can use this initial pose to create a graph by assigning a node to each pose of the robot. As the robot moves through the environment, its pose changes, and consequently we can add a new node to the graph with the new position of the robot as estimated by the odometry system. To connect these two nodes of the graph, so these two poses of the robot, we can use an edge that indicates the distance between the two robot positions as estimated by the odometry. In other words, these edges impose a constraint on the graph, a constraint that fixes the relationship between two nodes based on the odometry calculation. Obviously, as the robot moves, not only does its pose change, but also it explores new areas of the environment, identifying new environmental features with its sensors, for example, with the LiDAR. These features that the robot identifies in the environment are called landmarks and are nothing more than distinguishable key points of the environment that are added to the graph. These nodes of the graph, along with the robot's poses, compose the full graph that we are creating and that will solve the SLAM problem. If we have connected two poses of the robot, so two nodes of the graph that were representing the robot poses, using the odometry motion model, in order to connect a robot pose to a landmark, we can use the sensor model, so we can use the model of the LiDAR. In this case, the edge of the graph that connects a node with the robot's position to a node with the landmark's position is called measurement constraint because it depends on the sensor reading, for example, the distance and the direction in which the sensor detected the landmark. And so on. As the robot continues moving in the environment, we add new nodes to the graph with the robot poses and new edges that connect each pose to the previous one based on odometry measurement. Similarly, as the robot continues to move and to explore new areas of the map, it also identifies new landmarks that we can add as other nodes, so new nodes, to our graph, and we can connect them with edges that depend again on the sensor model that measure the distance to such landmarks. In this way, we obtain a graph in which the nodes represents both the robot's position and the environmental landmarks, and the connection, so the graph edges, represent both the odometry measurement between two robot poses and the sensor measurements between the robot pose and the landmark. Aren't we forgetting something? By creating this graph, we are neglecting that the odometry measurements are noisy, are affected by errors, and similarly, we are also neglecting that the sensor readings which identify and measure the landmarks are also affected by noise. To understand how the graph SLAM algorithm takes into account such measurement errors, we must think of the graph constraint not as rigid, immutable bounds, but somewhat like springs. They can vary, they can stretch, or they can compress as needed by the system, helping us to take into account for the inevitable measurement errors both in the odometry calculation and in the detection of the landmarks. Indeed, as we will see in the next lesson, during the creation of the graph, It is constantly subjected to an optimization process that seeks to produce the optimal graph, the one that best represents the robot trajectory and the environment landmarks, and eventually corrects measurement errors by simply compressing or dilating these springs so the graph edges